Thank you so much, everyone, for joining. Today's talk will be about how you can use ScaleDow to train a knowledge with to train a model using knowledge distillation. And then in the end, what we'll try to do is I've set up like a Raspberry Pi here. So what we'll try to do is I'll give you access to the Raspberry Pi, and hopefully if everything works, you'll be able to take a model that you've trained today during this session, and then deploy it on the Raspberry Pi, and like run it on the Raspberry Pi. Yeah, so I hope that sounds exciting for you. Before that, just a few things. So we want to thank all our tinyML strategic partners. So they are Analog Devices, Aeon Devices, ARM, DeepLight, Edge Impulse, EMSA, PhotaHub, Greenwaves Technologies, Probability Inc., IBM, HOTG, Imagimob, iTemis, Clicker Tech, Microsoft, Nota AI, NXP, OctoML, Prophecy, Kixo, Qualcomm, Reality AI, Ericsson Technologies, Renesas, SAP, SensiML, Silicon Labs, Sony Semiconductor Solutions Corporation, ST, Stream Analyze, Synaptics, Synsense, Sentient, and TDK's InvenSense. We also have a few other events that are going to happen. So one of them is the tinyML on-device learning forum that will be chaired by Dr. Danilo Pau, and it'll be happening on August 31st to September 1st. So you can either scan the QR code or visit this link to learn more about it, and and we hope you join us there. We also will be having the tinyML Neuromorphic Engineering Forum. That will be happening from September 27th onwards. And just like before, you can scan this QR code or go to this link to learn more. And yeah, we hope you join us there as well. Finally, we will also be having the tinyML EMEA Innovation Forum. So this will be in person in Cyprus Grand Resort in Limassol. We will also be joined by Massimo Banzi as well as Alberto Sangiovanni. And registrations are open, and you can register by going to either this link or by scanning this QR code. And exciting news is our meetup community has actually recently hit 11,000 members in 37 different countries, and there are 46 different groups. So yeah, to join a meetup community, you can go to this link here. Our LinkedIn page also has 3,000 members and 8.4K followers, and you can join us on LinkedIn by going to this QR code or this link. Finally, you can also subscribe to our YouTube channel, and all the events that we have will be recorded and uploaded here. And the link is youtube.com/tinyml. We have like nearly 7,500 subscribers, more than 440 videos. So yeah, so with that, I think I'll just introduce myself first. I'm Soham. I work as a lead ML engineer at a fintech startup in Singapore. So I like to tell people that, even though my day job is deploying like these really large models to, really complex computing systems and, in different regions all around the world, after my work, like my passion is to deploy those same models on tiny computers and, Raspberry Pis and stuff. Yeah, so that's a bit about me. So yeah, getting started. So what we'll do is, and yeah, apologies for the typo here. What we'll do is we'll first introduce knowledge distillation, tell you how it works. Then we'll also talk about like what are some of the advantages and disadvantages of knowledge distillation. and how you can, use ScaleDow to perform knowledge distillation. We'll also hopefully, test a knowledge distillation model that you have trained on an embedded device, which for today is going to be like a Raspberry Pi. And then in the end, we'll hopefully talk about some resources and some research papers that you can read to learn more about knowledge distillation. I think also like in like our next session, and Archana can talk more about when that is scheduled. But yeah, for our next session, our plan is to actually use ScaleDow to kind of implement a research paper and just show you like how easy it is. Like it's easy to do, like get something up and running quickly, but it's also like you also get those low level tools to also do research and more in-depth experimentation. So yeah, so with that, before like we usually like we've talked about ScaleDow a bit on this forum, but just to kind of tell you more about it again. Our idea, so we've kind of realized that with the ongoing like hardware shortage and tinyML being like this new field that's kind of a bit niche, it's kind of hard for people to learn about tinyML, and once they do learn, it's kind of hard to also buy the devices to actually implement some of the stuff you've learned, right? Um, uh, and and so our goal is to kind of make learning tinyML simpler. And we are trying to do that by creating like educational material, so like books, blogs, talks like this. And then we are also trying to build like a hardware library, so that you can also borrow some of the, so just like a normal library, you can borrow hardware, and then take some of the concepts you've learned and actually use them on the hardware. We're trying to do that by building a framework that you can use to optimize your models and then benchmark them, and also do some simple deployments. And yeah, and then hopefully you build some projects with it, and then that kind of contributes back to the education, if you write blogs and stuff. um, our goal is to be kind of framework agnostic. So we're trying to support all the common frameworks that are available. So PyTorch, TensorFlow, and OpenVINO and TensorRT. And we're also trying to support all of the optimization techniques available across these different frameworks, right? So our goal is like you can take like a model that's, let's say, trained in PyTorch, but then also use TF Lite's quantization, and then deploy it to like an Intel device using OpenVINO seamlessly, right? That's our goal. And we hope that by being able to do that, it makes it easier for people to learn tinyML and also get their hands dirty and build stuff easily. So yeah, and actually, like knowledge distillation is kind of like one of the first things that we're trying to support, because it's actually pretty hard to get knowledge distillation to work properly. Maybe I can talk a bit about why it is so hard later on. But before that, maybe I can talk about why we actually need to perform knowledge distillation, or why we need to actually optimize our models for before we deploy them to edge devices. Um, it's because like compared to like, let's say, a laptop or like a PC, which can have like GPUs and like even if not GPUs, but very powerful CPUs with multiple cores. These microcontrollers and microprocessors as well, they don't have all of that, right? They're just very simple devices, and they're meant to perform like simple and small tasks. Running neural networks on them is kind of not what they were designed for. So if you want to run a neural network on them, you'll have to first of all reduce the size of the model, so that it fits on the device itself, which can sometimes have only a few kilobytes of memory. And also you need to kind of shrink the number of operations it takes to execute the model. This way the model can be executed faster, Also, another kind of side goal of optimizing is to also take like complex layers and complex operations and like make them simpler, because a lot of microcontrollers don't actually have the hardware and the instruction set architecture needed to run those complex operations, right? Or it might just be too complex to run it on them. So yeah, so there's like different classes of optimization algorithms. So some algorithms like help you to save memory. For instance, pruning is one of those. And there's other algorithms which help you to reduce the number of operations. And then an example of that is early exits. Quantization, there's like different types of it. Like for instance, if you just do weight quantization, then you'll get memory savings, but then not a lot of like basically no compute savings. So there's not a lot of algorithms that can do like both, right? That can help you not only save compute, but also reduce the module size. There's only like two that are really popular. There's weight and activation quantization, which is like really popular. TensorFlow Lite supports it. But there's also knowledge distillation. And today, like, we'll be talking about knowledge distillation. So how does like knowledge distillation really work? So it's kind of it's actually like theoretically it's kind of really simple. The idea is we take like a really large model that has been trained on some hardware device, like usually like a very powerful hardware, like on a GPU or something. So this is like your ideal model, right? It's well trained. It's really accurate. It has it's working how you would want like the final deployed model to work, except that it's very large and you can't deploy it on a small device. So we call this larger model the teacher model, right? The reason we call it the teacher model is because what we do in knowledge distillation is we use this teacher model to train a smaller student model. So we try to transfer the knowledge that the teacher has learned on into the student model. This smaller student model is not trained; it's just like initialized randomly, and we train it using the outputs of the teacher model. So I hope I didn't make that too confusing. But that's like a very like top level like architecture of knowledge distillation. If we want to kind of go a bit deeper as to how the training actually happens, um, so think of how you make predictions using a model, right? So usually you feed in like some data into the model, right? Like in our case today, we'll be doing uh, computer vision. So let's say you feed in like an image, and then once you feed in an image, you get the predictions, which are usually like the probabilities that the model assigns to all the different classes, right? Um, so these probabilities, we call them the soft labels, because because we call them soft because what we actually need is like the hard labels, which are the predictions, right? So we don't really need the probabilities when we're actually doing inference. What we need is like something like 000 and then 1 and then 000, where the 1 corresponds to the actual prediction, right? So we get that usually by taking like the max of all the probabilities, and we call that the hard labels. um, the problem with hard labels is that they usually, like uh, uh, don't have a lot of information associated with it, right? For instance, the soft labels, which have the probabilities, can carry more information with it. So an example would be like, let's say the model found for an input two classes very similar. In that case, their probabilities might be actually like very close. So like, I don't know, one could be like 25%, the other could be 35%, right? Um, and and that gives us more information about, like, which classes are similar, and also more information about how the teacher kind of learns internally, right? How what it has learned. um, and we call this the hidden knowledge of the model, right? So when we try to teach a student model, we want it to learn not only like the predictions that the teacher made, but ideally also like how the teacher came to that prediction, right? And so we, instead of using like the hard labels, we use the soft labels to train the student. And our goal is at the end, like, to that hopefully the student is able to kind of mimic the teacher model, right? Um, yeah, so I'll stop there because I know like we've covered like a lot of information. If there's any questions or something, I would love to take a few now.
Yeah, I think there's one question already. So is
Mhm.
there distillation with more than a single teacher-student chain?
Yeah, actually, so that's a good question. So there's a lot of like teacher-student architectures and how you can train the student. So one of the architectures where there's like more than a single teacher could be like, let's say you have an ensemble of models, right? So you've trained many models to make predictions, but then you can deploy all those models to a single device, right? Like a small device. So what you do instead is you train a single model from the ensemble of models. Um, there's also like situations where you don't have a student model, where the teacher itself is the student. So that's called like self-learning, and it's also a very interesting paradigm of knowledge distillation. But for today, what we'll do is we'll just focus on just like the very basic knowledge distillation, which is where you have one teacher and then one student that is learning from that teacher. Um, Another interesting paradigm of knowledge distillation is where you use not only like the outputs from the teacher to train the student, uh, but also um, the inputs from in between the teacher. Sorry, the outputs of the intermediate layers as well. So that also kind of gives the student more, information to learn from, because it has not only like the information of what the teacher predicted, but also like how it got there, right? So that's also another interesting paradigm. Yeah, knowledge distillation is like my favorite like algorithm because it's so simple, but then you can do a lot of things with it, right? And it's also like very interesting how you're able to transfer this knowledge from one model to another, right? In fact, like there's so this paradigm that I talked about, where you take outputs from the middle, that was actually used like something similar to that was used to train, like, let's say the Inception model, the Inception like ImageNet model, to train that. There's also like a lot of cases where the student model is actually even more accurate than the teacher model, and we'll talk about how we can get there as well. Yeah, so I see we have another question, but maybe I'll take that a bit later.
Uh,
Um,
yeah, but you can let them know, nevertheless, like since the
yeah,
question.
sure. So I was going to cover that later on. But okay. So the question is like, is there support for knowledge distillation in all ML frameworks? So like you can use all and like most ML frameworks to train knowledge distillation on, but then there's no like API for it. So for instance, like in TF Lite or something, you have an API for quantization, right? Where you can just give a model and then TF Lite will quantize that model for you and give you like a quantized model. In case of knowledge distillation, you have to kind of write the whole um, algorithm by yourself, which is, and we'll cover why, but that is like a bit tedious, and many times it's very difficult to do as well. Um, Also, knowledge distillation, it's like a very finicky algorithm, and sometimes it doesn't work that well. And so our hope is we provide you with like some high level APIs that that you can use to get it to work well without too much effort. Yeah. Um, so how does knowledge distillation like actually work? Right. So what when you train like and some a question you might have is like, hey, if the student model can already learn and be just as accurate as the teacher model, why do we need like the teacher model to train it, right? Why can't we just train it on its own? And the reason, and there's a lot of theories around it, but the one that kind of makes the most sense to me is that when we train like a large model, we give it like a lot of layers, a lot of parameters. And that kind of helps the larger models learn faster and learn better, right? But at this and they can do that because they have all of these extra parameters to learn with, right? Um, Whereas if you use the student model and train it, it doesn't have those extra parameters and it's not able to learn as well. Um, so um, so 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 it's actually easier if we let the teacher model like learn and then try to distill what it's learned to a smaller model. And we can help it do that by at first like getting the student model to kind of mimic what the teacher is predicting, and hopefully in the process it forms an internal representation that is closer to what the teacher has learned, but it's like learned it like in a better way. Just like how like let's say like me as like or like if you've taught someone before, it might have taken you like let's say I don't know like 1 year to learn a concept. But then after you've taken that much time to learn it, you've kind of formed these mental models of the concept, right? And then when you teach the student, you take those mental models, you make it simpler, and then teach the student. And that's also kind of what's happening here as well. Um, so, um, so we've kind of talked about how it works from a high level, but how does it actually work from an algorithm perspective? Um, so how it works is, let's say we have a teacher model, right? And we feed it some input X. We also have another student model which is smaller than the teacher model. So we feed both of them like the same input, right? And then we get the prediction at the end from both the student as well as the teacher. But what we do is we calculate like unlike a normal training paradigm where you would take the corresponding label of X and use that to train the student. Instead, what we do here is we take the soft labels from the teacher and use that to train the student model. Um, and we find like basically like the loss between the soft labels from the teacher and the soft and the predictions of the student. We call this loss the distillation loss. So you can think of the distillation loss as how well the student is able to mimic the teacher, right? But like at the end, we kind of don't want the student to just be able to mimic the teacher. We wanted to be able to give like good predictions as well, right? So for that, we also, for the same input, get the hard predictions. And then, we calculate like the normal loss. We call this the student loss. And we calculate the student loss with like the hard labels, right? Or with the ground truth. But we actually don't use the student loss for training. We just use it for us to get an idea of how well the student is training. Um, so one thing that you might be wondering here is, um, if I'm training the student with just the labels from the teacher, and I'm not actually using the hard labels anyways, apart from just giving us a signal of how well the training is going. Can I train the student model on unlabeled data? So data with no labels, but we can use the teacher instead to generate like pseudo labels. And yeah, you're right, we can actually do that. And that's actually one of the advantages of knowledge distillation, which is we can actually train the student model on unlabeled data, or pseudo labeled data, and like the labels we get from the teacher model, right? And the models like EfficientNet were actually trained with this paradigm. If I recall correctly, I think EfficientNet was actually trained using a dump of Instagram images. I could be wrong, but it was either that or like another paper. Anyways, I'll confirm at the end. But yeah, there was this paper where they had like a trained teacher model, and then they had like a student model. But that student model, they trained it with label data, but also like a dump of Instagram images, which has no labels. And by training on that, the student model actually uh, had like got like a higher accuracy than the teacher model. So that's really cool. And also finally, you get both memory and compute savings. But this kind of comes like at a cost. So as you can imagine, like here, you're kind of dealing with like two models. You have two losses, and then you have to kind of make sure that you feed the same input to both models. You have to make sure you're comparing the right things. So it's kind of difficult like to set this all up, right? Because you have to keep track of all these different pieces that has to work together. And like let's say you want to actually like operationalize a training paradigm like this. That's also very difficult to set up, right? Because of all the different moving pieces. How you and how you also design the student model, and how you train the student model can also affect the accuracy of the student model. And training a model with knowledge distillation doesn't really follow the same kind of conventions, or it doesn't look similar to how you would train a normal model. So for instance, like let's say for NNIST, if you have a decently sized convolutional network, um, you could probably get like really good accuracy in like 2 or 3 epochs. And after that, it'll start overfitting, right? But then with knowledge distillation, you have to kind of keep at it, like keep training for a much longer time than you would, usually train a model. That's because knowledge distillation takes some time to work. And during that process, you might think like, hey, I'm training this model for such a long time. It's probably overfitting or something, but it's actually not. That's just how like the training works. Um, yeah. So I hope that makes sense. Uh, I do see like a few questions. Maybe I'll answer a few of them before moving ahead. Um, so one of the question is labels for hard prediction is 0 or 1 in contrast with soft labels. Yeah, so I think if you're talking about here, hard labels are the, yes, one hot encoded labels. So those are like zeros and ones. Yes. Um, And then the next one is for inference testing of the student model, do we still use soft labels? No. So that's the thing, right? At the end, we want the student model to work like a normal model. And so when we actually do inference, we use the hard labels because that's what we want, right? So yeah. Uh, okay. Moving ahead. Uh, Okay, so knowledge distillation via ScaleDow. So why, um, why do we think like it's easier to use ScaleDow? So first of all, because like, and we'll show you the API like in some time. It's very easy. It's just like 2 or 3 lines of code. And because it's two or three lines of code, you can actually quickly run like small experiments just to get an idea if the if knowledge distillation will work for you, right? Like train a quick baseline model, get some predictions, see if it works, and yeah, do that quickly. Um, Also, like I mentioned before, knowledge distillation is kind of hard to get it to work properly. So that's why we kind of provide like a high level API that helps you learn easily. Like that helps you uh, use the student model, like learn, like teach the student model easily. But at the same time, we don't, me and Archana, we are both like, we both have like research backgrounds, and what happens when you provide a high level API is that you can't actually tune the smaller nitty gritty parts of the algorithm, right? So our goal is to give high level APIs for students or beginners, or just someone who wants to get quick results. But at the same time, we also want to provide you with those low level APIs so that you can tune the algorithm as much as you want. Um, yeah. So with that, I think I'll like start with the demo. Yeah, so I think Archana, you could maybe post the link to the notebook in the chat. Yeah, so how you do it is okay, if you want like the latest like the latest update of scale down, and there's a chance that it might not work, you can always install it using Git. But like if you want the version that actually works, you can just do pip install scale down. um, and then you just have like two like very simple APIs. So one is we import like the knowledge distillation class, and then we also just import scale down as is because we need to load the model that you're using into scale down. We'll also use so for today we'll use TensorFlow, like two TensorFlow models. So that's why I'm importing TensorFlow as well, and we'll use NumPy just for manipulating the images. Um, Okay, maybe I'll just share the link to this. Yes, Archana has done it already. Okay. Thank you, Olga, for sharing. So it's a view only, link. So what you will have to do is like make a copy in your own Google Drive before you can run it, right? Um, And when you're running it, just make sure we're using like the latest version, which is 0.0.5. Uh, it's 0.0 because we are still kind of experimenting with the API and it's not perfect yet, but yeah. Okay, so we'll train something simple and fast. So we'll train an MNIST model. Um, and we'll just do some simple normalization by dividing it by 255. So the first model that we need is like the teacher model. So this, I've made it like a biggish model with two convolutional layers and then at the end like two dense layers as well. and I've trained it for like 2 epochs, and we have a final accuracy of 98%. After that, you can save the model as like the teacher model, and then we create like a student model. So this is a much simpler model with one conv layer, but it still has the two dense layers at the end. Feel free to like play around with like both the teacher model architecture as well as the student model architecture. Um, they don't really have to be like similar. For now, you can just like, we'll talk about like maybe in a later session how you can design the models to work better. But for now, just feel free to play around with the different number of layers and the parameters and so on. This is something that I've used for me. One difference that you'll see with the student model is that we're actually not running like the dot fit function. So we're actually not training the student model. I'm just going to compile it so that Keras knows, like Keras initializes it with some weights. And then I'm going to save it, right? So that's all you kind of need to do. So yeah, so the next step, like which is with ScaleDow, is we first like load the model. So ScaleDow can kind of load the model with like any type of model you feed it. For now, we support TensorFlow and PyTorch. So yeah, so just specify the kind of model you're loading. You can also actually load the model like directly. So you don't have to actually like save it and then, and then give it like the path or something. You can just give like the student model object directly as well. But yeah, that's fine for now. You can just load it from the path. Next, I've kind of made like a simple function that will just create batches of train images and train labels. So I've used a batch size of 32. Again, this is like a hyperparameter, and feel free to like tune it. And yeah, so now we can start training our model. Um, so how the training API works is you have to specify like all the different optimizers and losses and all that you want to use. So here I'm going to use like the Atom optimizer. Um, and then so for the distillation loss, usually we use something called the KL divergence loss. This is like the common loss used for knowledge distillation. And then finally, we for the student loss, we'll just use what we normally use, which is sparse categorical cross entropy, right? So next we'll initialize an object of knowledge distillation with all the different like pieces that you need to kind of train using knowledge distillation. So you need like the teacher model, you need the student model, you also need the optimizer, distillation loss, and student loss. You can actually also specify a lot of other um, pieces here. So for instance, if you look at the docs later on, you can specify, for instance, like other parameters, like let's say the temperature, or like there's also another parameter called alpha, which we haven't really talked about here because it's kind of yeah, it's these are those low level parameters that I was talking about before that you can also specify. But here it just like we've just taken some default values. Yeah. And yeah, so all you have to do is kind of basically loop through the number of epochs you want to train, and then loop through your training and training images and labels, and that's it. All you need to train your model is just call kd.trainStep with the data. It's actually that simple. So basically, it's like one line here and then another line here, and you'll loop. All this extra stuff is just like what you need for training anyways, right? After each training step, we can actually compile the student model and then see its accuracy. And you can keep training longer if you want. And then at the end, we can print all the different losses. So this is what the training looks like. So you can see after the first, so you can see like the loss is decreasing. And I could have trained it longer, and the loss would have kept decreasing, but for now I've just kept it at 5 so that it's faster. And yeah, you can also see that the accuracy is also increasing, right? And again, like remember internally what ScaleDown is doing is it's taking, like it's making sure it's doing all of this. Basically it's taking the teacher model and making sure it's only training the student model using the soft labels from the teacher and not like the actual labels. It's making sure that it's using the distillation loss for training and not like the the distillation loss, yeah, for training and not like the student loss or something. Yeah. Um, and yeah, so once the model has trained, you can just, get the student model by just saying kd.student, and then compiling it and get the accuracy of which is 95%. So here you might be asking like, hey, like what's the point of using knowledge distillation if my student is like less accurate than the teacher? Well, you have to kind of understand that the student model is smaller. So again, like uh, it's not like, it might not train as well as the teacher model. Also, because of how knowledge distillation works, you have to kind of keep training it a bit longer. Here you can see I've kind of stopped the training early. The loss was like still decreasing, and I could have trained it further to get better accuracy, right? So yeah, so I hope that you had a chance to like run this whole notebook, and hopefully after running you should see that you have a student model as well as a teacher model. Um, so to run the demo on the Raspberry Pi, what I'll do is I'll send you like the Raspberry Pi. What I'll do is I'll send you a link that you can use to access a Jupyter Lab server on the Raspberry Pi. Um, so for me to be able to do that, I need to kind of add all the participants here as like users in the in Jupyter Hub. So please like give me a moment while I do that. In the meantime, you can run the model and sorry, run this notebook and train your student model. Feel free to play around with the different hyperparameters. Train it for longer and so on.
Yeah, I know we have a couple of questions already, but feel free to drop us more questions. Again, this is like an open source package, so we are not, it's mostly like, you can also check it out. It's nothing that's happening behind the curtains. We basically pushed all of the code out, so you can check that out. You can suggest changes, and you can directly use the source code as well. But yeah, feel free to let the questions coming. Any feedback, any comments, you can also post that on the chat.
Yeah, so it's running like on a Raspberry Pi, and we have quite a few participants. So yeah, just give it a moment while I start all of your servers. Um, so how you can access it is, so I'm giving you a link to an ngrok link. I know it looks like it's like a phishing link or something, but it's not. Um, and so what you do is you go in there and it'll ask you for your username and password. So what I've done is I've set up your first name on like how you've logged in. So your first name. So if you look at your first name as a participant, so that's your username, and then the password is scale down. scale down, like everything is in small case. Same with your username, even if your first name has a capital letter, I've like made it all small. Yeah. So once you go in, please try logging in, and yeah, let me know if you're having any issues.
Yeah, maybe you can share your screen so that folks
Yeah.
can
So
can't
before I
log
do
in.
that, I want to also give you access to the notebook as well on the server. So give me a moment while I do that. Yeah, you should be able to log in and see a screen that looks something like this. Um, and what you'll see over here is a notebook called KD demo. So what you can do is you can actually click this button and then upload the model that you downloaded, right, from your Jupyter notebook. And then, yeah, and then all you would have to do is just change the name here. So what I'm doing here is, you may have to install TensorFlow and Matplotlib. I'm not sure, chances are it's already installed, but in case it's not, just run this cell. So yeah, so all you would have to do is just import the different packages, get the MS dataset, and then load the model. This is just a function that kind of prints like an image with the label. So in this case, like 2 and 2. And then yeah, all you would have to do is like run the prediction, and it should give you the prediction. So yeah, so let's see if it works for me here. Um, Not using the teacher model. Yeah, so here just like give an index, so I don't know, 100, whatever. So the 100th image is a 6, and hopefully it predicts that correctly. Oh no, yeah, just I think I forgot this. Is make sure you import numpy as NP. Import it somewhere at the top here. And yeah, so yeah, it works. I hope it worked for you as well. In case it doesn't, feel free to raise your hand or send us a message in the chat or something. Again, it's all running on the Raspberry Pi, and yeah, I think there's already a few people running it because it's getting quite hot. Um, but yeah. Um, I think like while we have other people working on it, maybe I can answer some of the questions.
Yeah, do you want me to let you know the questions?
Yeah, sure.
Yeah, so first one is how to be sure that over parameterization does not happen.
Okay, so if you're talking about like the student model, yeah, you can't really be sure. I don't think there's like I don't think there's a formal like method to make sure it doesn't happen. But what you can do is make your model like small, and if you do that, then yeah, then chances are you're at least reducing over parameterization. Yeah. Okay. So the next question is whether teacher model needs any similarity with the student model. Yeah. So in that case, no, not really. You can use any student model architecture. In fact, like as I was saying before, right, you can use like an ensemble of teacher models with multiple different architectures and train like a student model with again like a completely different architecture, and it should still work. Yeah. So yeah. So it doesn't really have to be similar. Okay. Another question is, Does ScaleDown work with PyTorch model? Yes, it does. I don't have a demo of that right now, unfortunately, but you can do whatever we've done like here. And instead of using Keras, just use just use a PyTorch model and it will work. So for instance, here, this line basically like everything remains the same, and that's kind of like what our goal is. Like nothing should change whether you're using a TensorFlow model or a PyTorch model. So everything remains the same. All you would have to change is like the losses that you use. So you can really use like a PyTorch, sorry, a TensorFlow loss with a PyTorch model. So yeah, so you'll have to change the different optimizers and losses, but that's like PyTorch related, right? So yeah, it'll work. You can also, we do have an API for changing a PyTorch model to a TensorFlow model. If like, let's say you're not comfortable with PyTorch, sorry, if let's say you're not comfortable with TensorFlow and you somehow want to change your PyTorch model to TensorFlow to get it to work, you can do that as well. So yeah. We have another question. Does ScaleDown work with cross-framework models like one TF-Lite and one PyTorch? Unfortunately, no. Like it has to be the same because that's kind of like how you can't really train like uh, different models with different that's been trained using different APIs, right? But what you can do is convert, like let's say the PyTorch model to a TensorFlow-like model, and then use it. You can convert it to a TensorFlow-like model, but you can convert it to like a TensorFlow model, train it, and then convert that to a TensorFlow-like model. You can do that. Um, okay. Which is the teacher model used by EfficientNet? Yeah, I can't recall at the moment. I'll have to check. Uh, okay. So the next question is training some models like SGB with soft labels takes a lot of time. One solution we thought of is to digitize soft labels such that the training labels are integers. Do you see any drawbacks with this approach? What techniques? Okay. That's interesting. So you want to change the labels with integers. Not sure how changing the labels will help with the training time because um, it's not really like um, the labels that are the issue here. You will still have to do backpropagation on the loss that is computed with the labels. So using integers as labels won't really do much um, for reducing training time. Unfortunately, with knowledge distillation, training time uh, is what you are kind of like is something that it's kind of like a part of the algorithm. It takes time for you to recoup that loss in accuracy because your student model is smaller. Um, with any other algorithm, right? There's always something that you need to that's like a disadvantage to it, right? So, for instance, with quantization, um, you can quantize your model, but it won't. You'll get like a drop in accuracy. So you will have to again like fine tune it to get that accuracy back, right? So it's the same with knowledge distillation as well, where you have to kind of train it a bit longer to get like good accuracy. What techniques would I suggest to reduce the training time? Yeah, that's interesting. That's actually something that I haven't really thought of. Yeah, feel free to like reach out to us on our Slack or something, and yeah, I'd be happy to like discuss any ideas you have. That's actually something that yeah, you could like work on as a research paper or something. Um, does ScaleDown support KD training of object detection modules? Uh, I haven't tried it out personally yet, but I don't see any reason why it should not. Maybe you could do it and then post like do a blog on it or something. That'll be really great. Um, okay. How scale down KD differs from Keras provided KD support? Keras doesn't have any um, knowledge distillation like API built in. You will have to build your own, like you'll have to write the whole algorithm on your own. Uh, yeah, so yeah, I'm sure there's like blogs or something that you can refer to. But yeah, Keras doesn't have any knowledge distillation API. And okay, one last question. What are the hyperparameter related issues can be expected while we do knowledge distillation? Um, so I think one like some of the issues that you get are some people don't use the same inputs often, like for the teacher and student model. So I've seen some training paradigms where you have one input, and what people do is they let's say they augment the image like 4 or 5 times or something, and then they don't actually, so to save time, what people do is they don't perform like get the soft labels with the augmented images. They just use the soft labels with the original image, which doesn't work that well, and the student model doesn't learn that well. Sorry. So that's something that a lot of people do often. Again, just make sure that your training time is high, and yeah, like you might see like your loss kind of starting to increase, but then it'll drop again in some time. That's also something that happens. We'll cover all of these. So there's actually a really nice paper on like knowledge distillation and how to get it to work well. And what we'll try to do in the next session is actually try to implement that paper, and yeah, hopefully like hopefully in that process the model you've trained here, um, you can train like a better model as compared to that. um, yeah. Okay. um, in the block diagram, how the soft label from the teacher differs from the ground truth. Yeah, so good question. So the soft labels, okay, so when you actually do knowledge like train, if you plot the output after after applying usually what happens is um, like the hard labels, it'll look like, let's say for MNIST, right, where we have like 10 images, um, it'll look something like this, whatever. Yeah. But then the soft labels, it might look something like this. So 0.1, uh, 0.6, and then 0.05, 0.05, and then 0.2 or something. Yeah. So I hope it adds up to 1. It should. Um, does it? Yeah, I think it does. Yeah. So it looks something like this. So obviously this has like more information than just the hard labels. So for instance, here you have information like these two classes look similar to each other or something like that. And then so like these two classes also look similar but not as similar as these two. and then this class is obviously the actual prediction. So this kind of gives the model more information. It also gives the model more information on how the teacher is computing, like coming to this answer, right? Like you could you could get to like a prediction like this using many different pathways and internal representations, right? But it's not necessary that but like because of that, like the student model and teacher model will be different. But if you give it the soft labels, then then it kind of learns how to mimic the teacher, and in that process, the internal representation becomes like closer to what the teacher um, has learned. Yeah, are there any other questions? Okay. Yeah, I hope you've been able to run, the models on the Raspberry Pi. Um, so we have like a few more slides. So, uh, so yeah, so if you liked the demo, and if you want to know how you can help us, um, so there's a few ways. So you can like request for hardware. That's something you can do, and we'll try to get the hardware to you, and you can try it out on your own. You can also like create blogs or something. So for instance, like someone mentioned about object detection. Yeah, would love to see like a blog on that. That's something that I haven't tried myself. um, we're also doing like research. So that's also something that you can help us with. In terms of like creating content, you can help us, help improve our website, and create like user guides. You can write blogs. You can publish a project, and then yeah, you can also attend like other present at tinyML conferences, or uh, even for tinyML Foundation, right? We're also doing research. So we're trying to like support some new algorithms like early exits. And we're trying to have like easy wrappers for people to use those new research algorithms. Um, we're also trying to work on model security. So that's very important for us as well, because on your Raspberry Pi, uh, it's very easy to like fetch the model that's running in here. There's especially if your device is located in a remote region. So we're trying to work on algorithms that can help increase model security. Um, and yeah, we have some ideas of the different kinds of papers that we want to work on. And if there's anything that interests you, feel free to reach out. And yeah, finally, you could also help us build the package. This is the link to the repo. And yeah, just pick up any issue, or if you see something wrong, just create an issue and start contributing. And I'd be more than happy to help you out as well. So would Archana. Or you can just add documentation. That'll be really helpful too. Um, so in terms of the roadmap, so yeah, we're kind of yeah. So in this quarter, we hope to publish like at least one research paper, and over the next few weeks, we will start to add support for quantization and pruning as well. And then by the end of the year, we hope to support tinyML ops, and then also like have some form of security support on in the framework as well. Um, yeah. So Archana, maybe you can like paste the Slack link. That'll be really helpful. Yeah. So
Soham, can you paste the Slack link? Unfortunately, I can't use the everyone on the chat. So can you paste it?
Yeah, sure. In the
Thanks.
meantime, maybe you can talk about the next meetups we'll be having.
Sure, absolutely. So yeah, hi everyone. We have a few meetups that are coming up. So what we're looking forward to is basically knowledge distillation, but using like a paper. So that is something that Soham will be talking about in our next session. So stay tuned at our meetup page. And Soham, if you could also drop the meetup link, that would be great so that folks can check that out. After that, we have planned one for quantization as well. And in the next one, we will also talk about, how exactly you can contribute to ScaleDown, because as you said, right now you have a lot of ideas. You'll probably, hopefully go and check out the framework. Again, it's completely open sourced. It's a Python package. But yeah, and I bet you'll have a lot of questions. So the next session will be how you can contribute. And then we will walk through like a research paper implementation on knowledge distillation. And in the following sessions, we will also cover like introduction to quantization, and then again cover like quantization like via ScaleDown, and also do a bit of paper reading. But yeah, thanks to everyone who joined in today and tried out the knowledge distillation. How long will that be running, Soham, or is it too hot already?
No, I can keep it running for a few more hours. No worries.
Yeah, absolutely. And feel free to reach out to us. We're there on Twitter, we're there on LinkedIn. So in case you have any questions, just feel free to reach out. It's a bit late in Singapore, but we will still be awake. So feel free to reach out in case you run into any issues. And yeah, thank you. Thank you again so much for joining in today. And feel free to ask us any questions, raise up your hands if you have any suggestions, feedback, anything you want to say. Thank you.
So thank you to all our tinyML partners. And then our executive partners, RNAI, Virtual Tech Talks, Edge Impulse, leading development platform for HML, Qualcomm AI Research, Sentient, making Edge AI a reality, and then our platinum partners, DeepLight, Flickr Tech, uh, Reality AI, Renaissance, Sony Semiconductor Solutions, our gold partners, Analog Devices, um, Hub, Latent AI, NXP, Seed Studio, SensiML, STM, Synaptics, Synsense, and our silver strategic partners. Yeah, thank you.